Welcome to the Fractional Calculus seminar. Today we have Professor Zhang, who is an associate professor of mathematics at Worcester Polytechnic Institute. His research interests include numerical methods for stochastic and integral differential equations, computational probability, and mathematics for machine learning. Before he joined in Worcester Polytechnic Institute in 2014, he received his PhD degrees in mathematics at Shanghai University in 2011 and in applied mathematics at Brown University in 2014. He co-authored a book with Professor George Kanadakis on numerical methods for stochastic partial differential equations with white noise. We are very happy to have you, Professor. You may please begin your talk.
Thank you very much for the introduction, and also, of course, the invitation for this seminar. I'm very happy to discuss with you the fractional calculus, especially in the past few years we've been working on spectral method for fractional Laplacian to deal with the singularity from a fractional Laplacian. The motivation. We are working with, the fractional advection diffusion equations. Their leading term is fractional Laplacian, and with some advection term, B could be constant or coefficient. But in this talk, I'm going to have just constant. C is also a coefficient. We want to know what's the difference between this one with the integer order, means alpha equal to 2, and and here, of course, the integral fractional Laplacian is defined in the principal value. So I think for this audience, this is pretty much very similar. So basically, it's a hypersingular convolution. You have x minus y d plus alpha of the reciprocal of this to be hypersingular. And we want to understand, if because of this singularity introduced by integral fractional Laplacian, so can we actually have a high order method? Especially when with the regularity in the weighted Sobolev spaces, can we actually do spectral methods? We know that it's going to be many methods can be low order, but how about the spectral method, especially if we know the singularity of the solution? What do we do, and how can I actually have any structure, singularity structure of the solution? We want to use spectral method to study this. Okay. This is motivated by solving fractional Navier-Stokes equation. This paper here is a 2018 paper. So actually talk about Navier-Stokes. What is different from the classical Navier-Stokes is at the fractional Laplacian on the right-hand side, so that you actually can take into account the turbulence, the largest scale in turbulence. So the C alpha is the so-called turbulence mixing coefficient. I think Mosen actually talked about this sometimes ago in the seminar. He has these boundary conditions, imperiodic boundary conditions. However, this is actually derived rigorously from Boltzmann kinetic theory. Well, of course, this is going to be on the whole domain, and how do we to solve them on the boundary domain, because we know the boundary domain problems are actually going to introduce in this singularity. One factor I want to use later on is actually try to use the Fourier transform of this fractional Laplacian, and this is, I guess, this is well known to the audience. I'll just skip this. So this is, well, I guess I will skip this because the audience actually is probably very familiar with this local the short jump, long jump models using fractional Laplacian, or simply talk about the fractional Laplacian. Some basic fact, very basic fact about this fractional Laplacian. Think about the fractional Laplacian here. So think about we have boundary conditions. Well, the omega here is a boundary domain, and U is we have this boundary condition outside the domain. Well, this is on the complement. This is already know that low regularity around the boundary. So for example, when g equal to 0, even if f is small, then you cannot really have Lipschitz continuous functions because the ux is in the form of 4, so which is a distance function to the power half alpha and times v. Well, basically saying, okay, ux is just Hölder continuous. Okay. Of course, v here will actually be determined by the regularities of v will be determined by the regularity of f, and if you have f equal to 0, g is non-zero. Well, basically you have a boundary data, then solution can be computed explicitly, and from here you can also have some singularity. Uh, so this is basically introduced to the boundary domain. So what is exactly known quantitatively? So in 2014, people have figured out the regularity up to the boundary. So for example, if you have this U is smooth on the whole domain, and then we can think about sorry, this S has to be to alpha divided by 2. So it says if you can actually U can separate the singularity around the boundary, which is delta, the distance function to the power alpha over S here, so you can actually see so the continuous the Hölder continuity can be bounded by the f in the L to infinity norm. Okay, and well, if you try to figure out using this regularity in the standard Sobolev spaces, so just use this Hölder continuity. This is very limited. This is 8 alpha, which is the fractional order plus the minimum half minus half over 2. So this basically will not go beyond 1.5, even alpha equal to 2. This means if we want to design numerical method, it means this is going to be very pessimistic. So basically, we're going to have method of order 1.5 in general. However, if you look at the shorter estimate, means you can looking at the ball, right? Think about the domain contains the orange, so that you have f is a little bit smoother, Hölder continuous with exponent beta. So and you can have C1, you actually the C1 in the ball, and also you can consider this. Okay, so Hölder continuous. So the alpha here has to be beta. So this is the beta with respect to the exponent of the Hölder continuity, and UX could be Lipschitz continuous for beta larger than 1 minus 2s. If s is larger than half, you can actually have beta equally can have first order derivative a little bit more. And you can even have derivatives. The derivative u in the ball is Lipschitz continuous if beta is smoother. So if we try to think about the local error estimate and also local regularity and the global regularity. So basically, we actually, we have somehow the idea of, solving singularities on the boundary, but, in the interior, so can we actually gain a little bit more convergence? So this actually motivates us to see a very simple problem that is on a ball. Okay, so if we look at on the ball, right? So think about u equal to 0 outside domain. And we can actually figure out the so-called pseudo eigenfunctions, eigenpairs. Many people in 1D, many people have to figure out what's going on for the pseudo eigenpairs. So basically it says, okay, we can have 1 minus x squared. Uh, this is the distance function, basically a distance function, power alpha here, power half alpha here, times this Pn alpha. So what is Pn alpha? This is a polynomial, a Jacobi polynomial with index, two index equal alpha. And in this case, you can take the fractional derivative and find, okay, this is, you guys still get the Jacobi polynomial. While this lambda n to the power 4, it looks like the pseudo eigenfunctions. So, and of course, we can see that the eigenfunction, the pseudo eigenvalues looks like n to the power alpha. And on 2D, right? So in the 2D disk, actually, we can think about, a spherical polynomials. So basically here, this is called Zonic polynomials. It says, okay, so in the R direction, you are going to still have this 1 minus R squared to the power half over 2 as the weight, and then you will be Jacobi polynomial with index half alpha and m. So this m here has to be related to the order of harmonic functions. And in this one here, then you can still have, if you work on the fractional Laplacian of it, you are going to have the fractional, the Jacobi polynomial, the same Jacobi polynomial, but with lambda. And m alpha is proportional to n plus m to the power half alpha. To the power alpha, so basically very similar to the first order, to the one-dimensional case. Okay. So we're going to start from here, try to see, okay, because we know this formulation, then these Jacobi polynomials are actually orthogonal, so why don't we set up spectral method? So all the reference I mentioned here in the first dimension, actually all work on about this. They have different ways of deriving the formula here. But here I'm going to use the basic idea, try to see, what will be going on if we use this formulation. Okay, so think about this problem with outside domain with Dirichlet boundary conditions, zero vanishing Dirichlet boundary conditions, and then we have, we're going to use U. Well, if you see my cursor here, un my equals to the weight function times the Jacobi expansion, while this un here is going to be the coefficient. And then, well, if we plug them in, we can actually get the fractional Laplacian. This un is actually summation of polynomials without this weight function. And then from here, we can actually design the spectral Galerkin method. So test this Vn using this weighted polynomial, and then, well, because the unknown is un hat, we can easily figure out un hat. So because of the orthogonality, we can actually figure out unk is actually just proportional to fk. The hat actually is going to be divided by lambda k to the power alpha. So this is going to be on this page here. So this means what? This means we can have a regularity guarantee. So what does this mean? So it means that if I have the fk exponentially decaying, so I'm going to have uk actually also exponentially decaying. So if you have fk algebraically decaying, so you are going to have uk algebraically decaying with a little bit of, again, in the order from this two constant here. And this, everything looks great, looks like we separate the singularity, and then, okay, we have, spectral convergence. But if we look at, low order terms, for example, if I look at the reaction equations. I'm looking at this is plus u with f, and of course I'll consider this boundary conditions of still vanishing Dirichlet on the outside domain. I can still use this this basis, well, this weighted basis, to see that well, we can still develop a spectral method. We can see, okay, this is going to be the first term here. Is going to be the one we see from the fractional Poisson equation. But because for the reaction term, we're going to have a full matrix here to see, okay, this is not going to be something we can figure out immediately. But after some calculations, we can actually figure out the UK would be, roughly speaking, this is 1 over k to the 2.5 alpha plus 1.5 divided by this orthogonal, the normalization constant. And here, I suppose that fk decays sufficiently fast. For even fk decays exponentially, I can only get this much. Okay. Decaying. So this basically thing there will be no regularity guarantee. Even you know the singularity is along the boundary, and you cannot have the regularity you had from the fractional Poisson equation. Uh, next, I am going to explain why this red term k to the power algebraic order is coming. So basically here, for those of you who don't know this polynomial, this is actually very naturally to associated with the weighted sublevel spaces. So what is different here is, basically if you have the weight, this omega here, you think about this as 1 minus x squared. So the same as the singularity term, but when you take one derivative, you're going to put it k here in the weight so that you can absorb some singularity from the derivative. So this is again, can be characterized by using the spectral equation. This is very convenient. So let's see. We have seen that if we use this form, right, to assume f has the regularity r in this weighted sublevel space, then we're going to have what? We're going to have the weighted u. So this omega here is 1 minus x squared. So basically u divided by 1, the distance function to the power alpha, half alpha is going to be is going to have the regularity alpha plus r. So where r is the regularity index for f, and u is going to have alpha more order than f. So basically, we can see that this is the regularity lifting we can see from the elliptic problems in 1D, of course. Well, if you want to see, how it works for the reaction equations, so then you can see that, the u, even you separate this singularity, 1 minus x squared to the power half alpha, then you cannot really see anything, even for very smooth f. So what we can hope is that alpha plus 3 alpha divided by 2 plus 1. Okay. Of course, this is minimum with r. So even r is infinity, you cannot really hope you have infinite different differentiable functions. So so we know that the intuition is like this. So if you have u equals to the singularity times v, so we can see that if you move the u to the right-hand side, f minus this weighted function times v is going to be, even v, suppose v is smooth enough, even this case, in this case, we cannot really expect too much because this weighted function here has very limited irregularity in this space. So this is basically 3 alpha divided by 2 plus 1. Okay, so this is where we can only have this 1.5 alpha plus 1. Okay. So this means that even we separate the intrinsic singularity, we cannot really get a better regularity. But this is still a little bit, this is better than what we can gain from the Sobolev spaces, standard Sobolev without weight. From here, well, we can continue to look at this, what's going on for the advection equations. We expect this advection equations, well, have lower regularity if you do the singularity separation. So basically the intuition is very similar if you think about, because of derivatives, u has the form of this blue term, 1 minus x squared with power half alpha, now minus 1. So this is going to be even worse, okay? So basically saying, okay, I'm going to have only 1.5 alpha minus 1. Okay, so this is what I can have here. So this is actually 2 order less than the fractional Laplacian with just lower order term, just reaction term. Okay. Um, so however, for the spectral method, we can easily verify that we have optimal convergence, just use the Milgram theorem, lemma, to try to set up the convergence. So this is what I can gain, right? So just a quick summary. So convergence means, the convergence order is the same as regularity. So when we have just diffusion without reaction terms, this is alpha plus R. So, and for the diffusion reaction equations, we actually only have, we can have alpha plus this 1.5 alpha plus 1. And if you have first order derivative, then it's going to be even worse. This is going to be 1.5 alpha minus 1. Okay. And the next thing is, okay, so this is somehow straightforward. Then what we want to do is want to verify this. For example, if you look at this diffusion equations, I want to set up this F is very smooth case. I want to see, okay, so what's with the convergence order? So on the right, I'm looking at the weighted L2 norm, which is from the error estimate. So we can see that this is 2.5 alpha plus 1. For example, if I look at 1.8, so 1 alpha equal 1.8, which is the red one, the bottom one. So I'm going to have 4 plus 1. So 2 alpha plus 1. So this is going to be weighted, this is a weighted autonom for the half alpha. Sorry, for the for the weighted, for the energy norm is going to be alpha plus 1, is going to be half alpha, alpha order less. If we look at this, um, the equation with fractional order, alpha, and also with this lower order term, first order term as lower order term. So even though the function f is very smooth, so we cannot really get better higher accuracy than this half alpha minus 1. Okay, so here, like we tested alpha equal to 0.1, 0.4, 0.6, 0.8. We can see that, this matches the convergence order, but, you cannot go beyond. So also here, I use the reference solutions n equal to 250. So you probably think it's too little, so too small polynomial order. So, but this is do in the past, well, probably several years ago, because of memory limit. So at that time, we actually try to increase the to reference order to increase the order in the reference solution. In this case, we have to do faster solvers, which I will show you later on. So very quickly. So so basically, we want to use a faster algorithm to calculate this without using the direct solvers. So basically, we can have n equal to, we use about 8,000 order polynomials as a reference solution, and then we test all this convergence orders. Everything looks perfect. So basically, for example, alpha equal to 1.2, we can have the rate is around 2, so which is exactly half alpha minus 1. This is what we have here for the first order. So of course, I also test some low regularity solutions, for example, sin x. You see that because of this sin x has limited regularity, 1.5 minus epsilon, so we're going to have this error, the order limited by 1.5, but you still can see the conversion order matched, thanks to the good property of the spectral method. So this is for sin x. Well, the next is, so we want to see that if we work with a very, very low regularity right-hand side f, so how can we actually derive this, excuse me, how can we see the conclusion? So will this conclusion change, or so next I'm going to consider this fractional elliptic problems with additive Gaussian noise. So so here I'm going to see, okay, I'm going to think about the reaction term u, and also I'll think about the BH here is the fractional Brownian motion. I will introduce the fractional motion in a second. I will just see that, okay, the regularity of this Brownian motion is actually h minus 1 minus h minus 1. Well, remember, h here is in between 0 and 1. So basically, we have negative index for the Sobolev's index. So can we actually expect some convergence? Okay. So what is then let's look at what is fractional Brownian motion. Fractional Brownian motion is is extension of Brownian motion by saying, okay, so if h is half, so we're going to have a Brownian motion, but if h is in between 0 and 1, so we are going to have the fractional Brownian motion. The covariance is functions like this, and the WH or BH dot is the derivative, is the formal derivative of this BH or WH. Okay, here in terms of spectral method, I'm going to use again the one we described before, and so everything is similar, but you have to truncate the fractional Brownian motion somewhere, and then so you can set up the Galerkin method, spectral Galerkin method, and then try to set up the convergence. Okay, so for the fractional Brownian case, we actually have the optimal convergence also. So we are going to have the convergence order is alpha plus h minus 1. So basically, it's alpha is the fractional order, h minus 1 is the regularity for the fractional Brownian motion dot the derivative of fractional Brownian motion. So basically, I think we are going to have optimal convergence. So if you h here, of course, this is going to be this is called Hertz index, is in between 0 and 1. If you have a little bit larger h, you can actually get a little bit better estimate in the energy norm. Here, of course, we have two parameters. We have to truncate the polynomial. We have to truncate the representation for the fractional noise. So actually, you can show that when m equal to n, you get the best convergence rate. Okay. So for example, we can look at the equal to 0.6, and we vary h. We're going to have alpha plus 0.3 minus 1 for the blue one. This is going to be order of negative 0.9. So For the red one, we're going to have 0.3, 1.3 order. So we can also vary as fixed h for when h is 0.9 is the solution. The fractional range motion is very smooth, and then we actually get a little bit better convergence. So everything looks fine. So also we have some result for the for another fractional noise, but I'm going to skip here. Um, so so here, well, because of the regularity we actually discussed. Uh, so it looks like we can get some of the singularity structures, because we know that in this case, with this zero order operator here, we actually have the u divided by this one, which becomes alpha plus half alpha, 3 half alpha plus 1. Okay, and we can calculate this 1 to the 1 minus x squared to the half alpha is in this case. Okay. And this 1 minus square to the power alpha exactly will match the one we have here if alpha is large enough. Okay, so we conject that so u of course divide by this weight can be written down as C1 constant plus 1 minus x squared to the power alpha. And then the next term, of course, the next term is hard to guess for now, but I want to guess this is very similar to what we know from the Mittag-Leffler function. So basically, this alpha minus this is fractional order, and the u is zero order. This is alpha minus zero. And similarly, we can get some singularity structure for this function for the fractional advection diffusion equations. Oh, however, so far I just have m equal to 2, but if we set f equal to 1, probably we can work out this later on. Okay. But right now, this is all what I get here. Okay. Um, so this is all about a 1D. 1D is clear, the singularity is clear, and what about 2D? Well, looks like a 2D case is very similar. So because of the pseudo-argument functions, so we talk about this, the polynomials times the radial basis, the radial direction, and this harmonic functions in the theta direction. So these are generalized uniform polynomials. They actually are complete orthogonal systems. You can still develop numerical method, but the thing is, this becomes a little more complicated in analysis. And again, I want to show you that if you have a very smooth F, you can still get very high convergence if alpha is large. For example, when alpha equal to 1.8, you can expect the red slope here, so which is 5.5 order. Okay. So of course, this order here is in the direction of alpha, and the theta direction with this is going to be very smooth. So I guess this is too complicated for the seminar, so I'll just leave here. Later on, I will leave the slides to you. So for interested audience, you can take a look, and the basic message of this slide is actually if you set up the same thing, say same basis, the basis from the pseudo eigenfunction and set up the spectral method, you can get optimal convergence. But the index here of the regularity is a little bit messy. Uh, Now I think I have about 10 minutes to we can talk about another two-dimensional application use spectral method. Well, not really a spectral method, but it's actually can be exponential convergence. So one thing we observe that is, if we try to evaluate the fractional Laplacian, we can use the Fourier transform. Okay, when so looks like how can we use it? Okay, so if we set up the basis, right, like a radial basis, so suppose then we can use this formula 14, try to set up this radial basis, and then from there we can actually see, all right, because this is a radial basis, and the Fourier transform is going to be also radial. And now I can actually simplify 14. So using this so-called Hankel transformation, and this is well known in many books and papers. But the difficulty here is if you know, even if you know the g hat here, this function, this integral is actually very hard to evaluate because this is the j here is the Bessel function of the first kind. So this is going to be high, oscillation, with this omega times r. Okay, this argument. So, and also you are going to have some singularity, weak singularity at omega equal to 0. So then how would we do this? So we find out, there called integration method. That actually can do this. This is the so-called double exponential transform that was discovered, invented, in 70s. So we can evaluate this very actually exponentially accurate. Okay, as long as g hat is actually is analytic. Okay. So with that, we can actually work on this the fractional Laplacian, and then the rest will be somehow straightforward if we work on this fractional Laplacian with low order terms. Okay. Here I want to showcase that for the fraction Poisson equation, how we do this and how we work with irregular domains. So here, what we do, think about this guy here. Now I have G is maybe non-zero outside domain. So I want to see that, okay, so how would we do this? So I have this fractional Laplacian. I want to put the boundary here. This boundary terms, which is omega tilde. So basically the idea is we want to see that, okay, I have an omega, maybe irregular. I want to find an omega tilde so that covers the omega. So, but omega tilde is very regular. So that I will put it back here so that I don't have to evaluate to sample along the omega tilde to the complement. So then I have to sample only on this omega, omega for the equation, and also this is uh, omega tilde here. The boundary is omega tilde minus this omega, the irregular domain. Okay. We're going to sample this. This is probably irregular, but the first one is very accurate to evaluate. So this is not, this is extension of some literature here. Unfortunately, I didn't have it here. Sorry, I will add this later on. So basically, we are going to have three sampling domains. One is omega, which we call this the interior domain. B is the boundary. Boundary means the boundary of omega, and E is the extended domain. So on the boundary of extended domain means omega tilde minus the closure of mu. I will give one quick example. So, for example, if we work with this sector, so basically we want to work with the green, the blue ones, the blue curve here, the blue curve enclosed region. So what we do is, okay, we can find a region, for example, this dotted dashed red lines, we can find the domain like this. We can show that we will sample using red, for this exterior domain, the extended domain, and the black points here on the curve, on the circle, uh, on the arc here. So, and then we will have this blue points on the in the interior domain. Okay. Because there are many ways to do the interaction, to do the extension, right? To have this domain omega tilde. So here we have three, right? So the first one is, okay, we want to see, okay, can we actually same thing? Okay, we just have another um, 3/4 unit disk, but with a little bit larger domain. This is my A. And the second one is the one I just showed here. So basically you're saying, okay, I'm everywhere here. So for the 3/4 of the circle, the disk, I'm going to expand a little bit, but for the rest, this is the L-shaped part here. I'm going to have just a little band here, so just rectangles. Uh, so this is the second case. The third one is just use a circle that bound bound the whole disk, and then you have to sample along all this the larger disk. So here I'm going to compare these two, these three from three extended domains. So you see that basically, this is too much to see. I know probably, probably this is, we can look at alpha equal to 0.2. So what we can do here is, okay, because the extended domain has different volumes, so we actually, we can actually should increase the number of into the domain collocation points in the interior extension domain. For example, A is probably the smallest, so has smallest extended domain, and B has a little bit larger domain, extended domain. C has the largest because this is the circle. It's a disk that contains this sector here. So we actually increase the numbers of collocation points. Then we can observe that a very similar convergence accuracy, but this is really not convergence because the solution is actually very very rough. This is y minus r squared divided to the power 3 plus half alpha matches a little bit of singularity of the solution. And here we actually use the Martin kernel with 0.5, 0.5. And if you try other method, other Gaussian or other kernel method, it gets very similar result. But the main message here is actually we can use the spectral method or radial basis method to work with extended domain and to get some accuracy. But if we want to see more, okay, accuracy, we need to work a little bit more. I think I'm almost out of time, so I will just stop here and take questions.
Thank you very much. That was actually very thorough. I have to come back to you at some point, looking at the results at the detail. For questions, please raise your hand. I'll call out your name in the order they appear in my screen.
Yeah, the talk is a little bit brief, but I'm happy to discuss these details later on if you are interested in the topic.
Yeah. I'm actually very much interested. I work on spectral methods as well for fractional. So recently I extended to general fractional operators. So the initial idea where you had this pseudo functions or what you call, what Mao had in the beginning of the slides that you had Jacobi polynomial times something.
Yeah.
So I'm using the same idea to construct Jacobi called convolution polynomials, which I'm calling it for general fractional operators. The paper is in archive right now. So it's following the same ideas. I mean, like the high level idea is not very different from each other. So yeah, so I'll have to look into a bit details
Okay,
of this
great.
work.
Great. Yeah, we can talk later. Yeah.
Yeah, yeah. So one more remark when you mentioned fractional Navier-Stokes equation. Historically speaking, if I am correct, Jacques Lyons probably introduced it for the first time. So basically, what he did was fractionalize the diffusion term. Uh, uh, and I think that the first person to do that is Jack Lyons. I'm not entirely sure, but probably yes. There is a talk by Daniel Brutus within this seminar series, and he gives a bit of historic review, and also the results, mathematical analysis results. But I also know the paper of Pushman and Epps, and Moxon's work. Uh, uh,
Yeah.
and there is another series of equations which are also called as fractional Navier-Stokes, which I call it fractional Navier-Stokes because the reason I call the other series of equation as fractional Navier-Stokes is because uh, the framework or the machinery that goes into is on a very similar lines as one does it for Navier-Stokes equation. That does it to derive Navier-Stokes equation, but then you're operating at a different scale. I mean, Navier-Stokes are uh, for every scale, and but if you want to look into coarse graining of it, then you have to talk about the about fractional Navier-Stokes. Not this fractional Navier-Stokes, the one I have it for. I have it. Apparently, the terminology, the name is the same, but it's very different equation. So, on the applied mathematics perspective, the challenge in that equation is that if you look into the Navier-Stokes, you have velocity and pressure coupled, right? Uh, but in that equation, in addition to velocity and pressure coupling, you have operators which are coupled. So so if you look into the Stokes problem, what you have is you also satisfy the divergence of the velocity to be zero, right?
Mm-hmm.
So in my case, I have the fractional divergence of velocity to be zero, uh,
Mm-hmm.
zero, and that fractional order is coupled with the other equation. So I'm not quite sure how to solve those equation at this point, but yeah, but I recently derived those equations. So yeah.
Okay. Yeah. So we have some work on this Stokes equation using RBF, use the radial basis because of the evaluation of fractional Laplacian. Also, you can work with different domains. And also you
Mhm.
can have divergence-free radial basis functions, and but we only have some preliminary results.
Okay, my understanding would be that in soup condition, it trivially satisfies, but I still want to see if somebody has made any calculation about it. Did you make any calculation about it?
Yeah, there are some paper there was a paper on the there was also using finite element, but actually they didn't actually explore what's going on. Um, for they actually test only some very simple solutions,
Hmm.
not in real applications. We try to extend a little bit using the RBF, try to see, well, can we actually observe, the different effects that the fractional Laplacian introduces.
I see. I see. I see. I see. Very interesting. Very interesting. Anyway, mm, anyway, so I'll get back to you if I have further questions, and then we'll see. Uh,
Yeah.
and meanwhile, if you have any questions for me, please do let me know.
Yeah,
So,
yeah. So
do,
it will be great if you can send me your work on the duration of the well, your version of fractional Navier-Stokes.
Sure. So I haven't actually written down the manuscript because every time I sit down to write it, it gives me a lot of anxiety because the claim is too big for me to handle. Uh, 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 so I have a talk right now at APS, but I also gave a talk within this seminar series. So if you look into the YouTube channel, uh, you
Oh,
will
okay. Yeah.
find my version of the equations, but my notations are everywhere. But okay, but
Okay.
I hope it's still understandable. But sooner or later, I'll once I draft my manuscript, I'll also send it to you.
Oh, that would be great. Yeah, yeah. Well, yeah. I will dig into the seminar series, try to see
Yeah,
it.
yeah, sure, sure. Does anybody have any more question, remarks, comments? You may please unmute your mic. Okay, I don't think so. I don't think so. So this is a good point to stop here. Thank you very much for the nice talk. It was very nice having you here.